Thank you very much for the invitation and for organizing this conference in such a beautiful location. I will tell you about one of the experiments in my group at the University of Basel in Switzerland. And in this experiment, we use an atom chip to prepare ultra-cold atoms, Bose-Einstein condensates in entangled states, more precisely in spin squeeze states where all the atoms are entangled with all other atoms in this cloud. And we use this system for explorations of quantum metrology and also as a starting point for experiments on quantum foundations with massive many particle systems. And in the talk today, I will tell you about some recent work where we split such a cloud of spin-squeezed atoms into multiple ensembles that are spatially separated from each other and can be individually controlled and detected. And this allowed us to observe the Einstein-Podolsky-Rosen paradox between two spatially separated massive many particle systems. And in current experiments, we have extended this to multiple clouds, and we are using such an array of atomic sensors for investigations of multiparameter quantum metrology. So multiparameter sensing is a new frontier in quantum metrology that currently receives a lot of attention. And this is because many sensing tasks are actually multiparameter estimation tasks. For example, when you want to sense multiple components of a magnetic field, two orthogonal components, like in such a quantum compass here, this involves estimation of multiple parameters. Another example is sensing or imaging of field distributions with an array of such sensors. You obviously want spatially resolved information, so you want to obtain information about multiple parameters at once. Another example is such a network of atomic clocks which compare time through quantum links. So while for single parameter quantum metrology, like what you do in an individual atom interferometer or atomic clock, we have a clear conceptual framework. These multi-parameter estimation tasks are surprisingly complex and come with a number of conceptual challenges. For example, in the case of this vector field sensing, the measurements that are optimal for the two magnetic field components do not commute. So you have to somehow compromise between them. In a similar way, when you have an array of sensors, although the measurements compute, you can discuss how you can use entanglement within each sensor or entanglement between the sensors to enhance the measurements of the local fields, or possibly also some parameter combinations, some linear combinations such as gradients or higher moments of the field that you are interested in. And in such scenarios, the quantum gain you can expect depends strongly on what kind of resources you have, what kind of entangled states you can make, whether you have local detection or just global detection. And so each scenario comes with different expected quantum gains, which are not always, depending on the resources, which are not always clear. So more generally, the question is, what are the optimal strategies in such a scenario? And these questions are currently investigated a lot, but most work so far is theoretical and there are hardly any experiments. So I will tell you in my talk first about our experimental system, a two-component rubidium BC on an atom chip. I will tell you how we produce spin squeeze states and use this for standard quantum metrology, quantum interferometry of a single parameter. Then I will tell you how we split such a squeeze BC into two clouds and that are entangled with each other and show the Einstein-Podolsky-Rosen paradox. Then I will show you how we extend this to multiple clouds for multi-parameter estimation. So this is our experimental system. At the heart of it is an atom chip which produces Bose-Einstein condensates close to the chip surface in magnetic microtraps. A typical scenario, to give you a sense of scale, is we are working with around 1,400 atoms at a few tens of micrometer distance from the chip. And currents sent through these wires create magnetic field landscapes that we can tune in time to transform a single well into a double well, to move the atoms around as a sensor on the chip, and so on. The atoms we are working with are rubidium-87 atoms. This is the ground state hyperfine structure. And in most of the experiments I'm going to talk about, we are working with these two states, the state 1 minus 1 and 2 plus 1. And they have the nice feature that they have the same magnetic moment to first order, which means they see the same trapping potential, and the spin degree of freedom is decoupled from the motion. And they're also very robust because any magnetic field fluctuations on the chip are common mode, and to first order don't perturb the coherence. We can drive microwave and RF transitions between these two states, see then Rabi oscillations with very high contrast. And this tells you already that the whole cloud of atoms is acting like one giant spin that is rotating with almost full contrast. To describe the internal state of this ensemble of n effective spin 1/2s, where the two states correspond to these two that we have trapped and that we can manipulate, we can introduce a collective spin description, where this collective spin is simply the sum of the individual spins of all the atoms in the cloud. And so the Z component of this collective spin is simply 1/2 times the atom number difference between the two states. And that's a quantity which we can directly measure by absorption imaging. So in a single shot of the experiment, we count how many particles we project the atoms in this Z component and count how many particles we have in each state. And we can do this by absorption imaging with a resolution of just a few atoms. So this is how we measure SZ, but we can also measure any other spin projection by first doing such a high contrast Rabi oscillation and then measuring SZ. So the quantum state of this collective spin can be depicted on such a sphere as such a fuzzy blob representing the quantum noise of the transverse spin components. More precisely, what you see here is the Wigner function of the state. And the state depicted here is a coherent spin state where the atoms are uncorrelated. So here they are not entangled, and then this quantum noise, simply the projection noise of n independent spins, scales like the square root of the number of the particles. And this is what gives rise to the standard quantum limit when you use the state in an interferometric measurement. An important ingredient of our experiment is that we can use atomic collisions to create entanglement between these atoms. And the collisions in our system can be made state-dependent with a state-dependent potential. This is a special technique. I don't have time to go into this now, but if you want to know, I can explain to you. It gives rise to such a one-axis twisting Hamiltonian. It's a Hamiltonian which is quadratic in the Z component of this collective spin. And if we evolve such a coherent spin state with this Hamiltonian, it gets twisted into a squeeze state, which now has a reduced uncertainty along a certain direction, and the other spin component is anti-squeezed. Now, this spin squeeze state actually features entanglement between the particles in the cloud. And this you can understand by realizing that the quantum noise of this collective spin is ultimately due to the fluctuations of the spins of these individual particles that make up the spin. And so if the quantum noise is reduced along a certain direction, this means the spins are anti-correlated along this direction. While along the anti-squeeze direction here, they are correlated, and so their quantum noise is enhanced. So you can see that by measuring the fluctuations of this collective spin, we can learn something about the correlations between the atoms in the cloud. This is again a Wigner function of such a spin-squeezed state, but this time it's not a simulation. This is the result of tomographic measurements. So we've produced such states and then projected along many different directions, measured the spin, the histograms of the spin fluctuations, and from this reconstructed the Wigner function here on this sphere. And you can nicely see there are certain directions where the spin noise is squeezed, and the orthogonal directions are anti-squeezed. And typically in experiments, we reach about 8 decibels of squeezing in this system. We can then use such states for interferometry beyond the standard quantum limit in a Ramsey sequence. So after producing the squeeze state, we orient it such that we can pick up a phase shift in the Ramsey interferometer along the squeeze direction. Then the final pi over 2 pulse converts this into a population difference and allows us to read out this phase shift now with reduced uncertainty below the standard quantum limit given by this spin squeezing parameter. And if we perform such experiments, this is the signal we can get, the interferometer fringes, and here you can see the noise, the performance of the interferometer with a coherent state and with a squeezed spin state. And you can see that this squeezing from the input state translates into enhanced precision of the interferometer. This is somewhat older data. In current experiments, we reach up to about 7 dB of squeezing. We can use this squeezed interferometer then to map out field distributions close to the chip surface. I don't want to go into too much detail. It's also the squeeze state is also the starting point for investigations of Bell correlations or entanglement patterns in this cloud. So this proved to be a very rich system. What I want to talk to you about now is how we can use this squeeze state as a starting point for experiments where we split into multiple clouds. And the question is, can we somehow exploit this entanglement between the indistinguishable particles in the squeeze state and distribute it between different spatial locations and then observe entanglement or even the EPR paradox between them? So before I tell you about these experiments, let me remind you of the EPR paradox, because it's, of course, a very foundational topic in quantum science. Let's consider a quantum system. In our case, it's a spin system, B. And because it's a quantum system, it has to obey an uncertainty relation, which in this case is the uncertainty relation for spin, which states that the product of the variances of two transverse spin components, Sy and Sz, cannot be smaller than 1/4 times the length of the spin along the x direction squared. So this simply derives from the commutation relations of spin and holds for repeated measurements on identically prepared spins. And this constrains how well we can predict the two orthogonal spin components y and z in this system. Now, if this system is entangled with another system, A, then we can make use of measurements and their outcomes obtained on system A to predict the corresponding measurement outcomes on system B. And this prediction can be cast in the simplest case, in the form of a linear estimate, where we simply take the measurement results obtained on system A, multiply it with a gain factor, add an offset, and this is then our prediction for the corresponding spin component on system B. We call this the inferred spin B. Now, what is the uncertainty of this prediction? For this, we have to do the actual measurement on system B and compare with our prediction. So the uncertainty of this prediction is what we call an inferred variance, and it's simply the variance of the difference between the actually obtained measurement result on B and our prediction. So that's simply the error, the variance of the error. Now, if the two systems are sufficiently strongly entangled, it can happen that the product of these inferred variances for two orthogonal spin components, which do not commute for system B alone, can be smaller than the Heisenberg uncertainty bound of the corresponding system. And this is what Einstein, Podolsky, and Rosen realized in 1935, that this allows you to make better predictions than what you can locally do for your system, even if you have perfect control. And from this, they deduced that quantum mechanics must be somehow in conflict with our everyday notions of locality and reality. Because it really means that somebody else having access to a system A can make better predictions about your system B than what you can possibly do with full local control and perfect detection. So this constitutes the Einstein-Podolsky-Rosen paradox, if you can observe this. You can turn this relation into an EPR parameter by dividing by the right-hand side here. Then you get this EPR parameter here, which you can measure. on your system, and if it's smaller than 1, you have the EPR paradox. So it's interesting to compare this EPR condition to an entanglement criterion, which has nearly the same form, but it has an additional term here in the denominator, which is always positive. So from this, we can see that it's always easier to observe entanglement than to demonstrate the EPR paradox. Or in other words, the entangled states that show the EPR paradox are a subset of all entangled states, or you need particularly strong correlations for the EPR paradox. And EPR experiments were so far mostly done in optics and also by imaging a single atomic cloud, but with 2 massive atomic many particle systems, it was not yet possible to observe the paradox. So in our experiment, we follow a strategy that is actually very conceptually closely analogous to the experiments done in optics. So the optics experiments that demonstrate the EPR paradox, they often use a squeeze state of light as a source of entanglement. Then this state is split on a beam splitter to create 2 EPR entangled optical modes, which are then measured by homodyne detection. You can measure the different quadratures of the light and look at the correlations between the 2 detectors. Our strategy to observe the EPR paradox in a many particle system is actually very similar conceptually. We start by spin squeezing the atomic cloud, which creates all-to-all entanglement between the atoms, which at this point, however, is only globally accessible because the particles are indistinguishable and there's no way how you can measure one or address one particle in the BC without talking to all the others. So what we then do is we do a beam splitting operation, a spin independent beam splitter that separates this cloud into 2 spatially separated clouds. And now we can individually address and locally rotate the spins and detect to see the paradox. For this, it's crucial to be able to do this splitting coherently in a spin independent way. And this is how we do it. We start by spin squeezing the atoms on the atom chip, like I've explained before. And then we split the cloud into 2 by a combination of hyperfine changing microwave pulses as a beam splitter plus Stern-Gerlach magnetic gradients. So we start with our initial 2-component system drawn in orange here. We do pi/2 beam splitter pulses to another set of hyperfine levels, which have a different magnetic moment. And then we apply a magnetic gradient to split into 2 clouds, each of which is now, again, a collective spin system composed of 2 hyperfine levels. And then once they're fully split, we can apply spin rotations to the clouds individually and then detect all of the states in time of flight. So this is a picture of the 2 collective spins that are entangled, and then we perform repeated measurements on identically prepared systems and compare the correlations. In some measurements we measure as Z, then in others we measure as Y, in others we measure as X, and so on. And in these measurements of SZ, you can see that the spin A and the spin B are anti-correlated. This is expected because that was originally the squeeze direction. And in SY, they are correlated because this was the anti-squeeze direction. At the same time, we still have a very high contrast along SX. And if we put that into the EPR criterion, we see that we have the EPR paradox. And this is the first time this was observed between 2 spatially separated massive many particle systems. So this is very interesting from a foundational point of view because it allows us to push somehow the limits of these EPR experiments to more massive, more macroscopic systems. But in the remaining time, I want to tell you how we use this capability for multiparameter metrology. And the scenario we have in mind here is the one of field sensing with a sensor array. So we have these multiple clouds of atoms that each can locally sense the value of an electromagnetic field. which is then imprinted as a rotation of the spin theta 1, theta 2, theta 3 on the individual clouds. And the resources we have is a fixed number of atoms in total and a fixed number of preparations of the system. And we have the ability to globally squeeze the entire ensemble. So that means the sum of all the individual collective spins here is squeezed. This is what we can do with our experiment. So these are our resources. Now, if we just squeeze the atoms and distribute them like this and imprint the phases, then it turns out the only quantity we can measure with quantum enhancement is actually the sum of all these parameters theta. That is simply reflecting the fact that only the global spin of the entire ensemble is squeezed. So only the sum of all the phases gets a quantum enhancement, and any other linear combinations as well as the local phases is not enhanced by the entanglement between the clouds. But we can make use of our capability to individually address and manipulate the clouds to apply, for example, local pi phase shifts to individual ensembles. And this transfers the squeezing from this symmetric mode of all the ensembles into modes where we can have minus signs in front of desired phases here that are imprinted on the ensemble. So in other words, we can transfer the quantum enhancement into any target Hadamard mode of these individual phases and obtain this corresponding linear combination with quantum enhancement. And then the strategy is clear. We can repeat the experiment and apply pi phase shifts to different clouds to prepare and measure a complete set of Hadamard modes, each with quantum enhancement. And this then also allows us to reconstruct all the local phase shifts simultaneously with quantum enhancement. So here the strategy is demonstrated for two clouds first. If we just split and don't apply pi pulses, then we see that only the common mode of the two phases is squeezed. So this is a plot with the two local phases, theta 2 and theta 1. And these are histograms of measurements result, as I've shown you before, for the EPR paradox, but now for two different phase shifts along theta 2 applied, and the distribution shifts. But you can see the states are most distinguishable actually in this diagonal direction, which is the common mode. If we now apply a pi phase shift to one of the clouds, these distributions turn around, and now we can sense the differential mode with quantum enhancement. And this allows us to do gradiometry, for example, which would be interesting for example, to measure with atom interferometers some gradients. But we can not only transfer the quantum enhancement into the plus and minus superposition, we can in fact transfer it into any linear superposition of these phases we might be interested in by not only adjusting the phases, but also the atom numbers in the two clouds. And this is what is shown here. So this is a varying distribution angle between these two phases. And you can see that we can transfer the quantum correlations into any of these linear combinations and measure them with quantum enhancement between 5 and 6 decibels. Now, this is what we can do with two clouds, but we can also extend our splitting sequence into multiple clouds. This is an experiment with 3 clouds, which sends 3 local phases. Here you can see the 3 atomic clouds. And what this plot shows you, this correlation plot, is different pi pulses applied on different of these clouds. So here, for example, there's only a pi pulse in the middle cloud. Here's one on the left cloud. Here's on the left and on the middle cloud. And depending on where we apply the pi pulses, different linear combinations with plus and minus signs of these 3 parameters get the quantum enhancement, always the corresponding configuration. And then if we perform multiple such experiments, we can actually reconstruct all 3 local phases simultaneously with quantum enhancement. And already there are some conceptually interesting things pop up. For example, it turns out that it's better to measure 4 linear combinations of clouds than 3 if you want to sense 3 distributions, 3 local phases. And that has to do with the fact that there is no Hadamard matrix in dimension 3, so you have to use a truncated version of the 4-dimensional Hadamard matrix to implement this sensing task. Okay, with this I come to the outlook. I've shown you experiments on the one hand on quantum foundations, the EPR paradox with massive many particle systems. There are many interesting directions to go from here. You can ask whether you can go from measuring the EPR paradox to a Bell test, which however requires non-Gaussian states or measurements. We have some ideas in this direction. It is interesting to explore the macroscopicity of the many particle EPR. You can ask the question, in which sense is this more macroscopic than an EPR test with individual particles, for example? There are first theoretical works in this direction, or we could study entanglement also in tripartite systems here. And then in multiparameter quantum metrology, this can be further developed to sense field distributions on a chip, and there are interesting relations to compressed sensing. If you want to know a certain subset of these parameters, you can get even higher quantum gains, or to explore networks of clocks. With this, I would like to conclude. This is a picture of the group, and in red, I've highlighted the contributions of people working on this experiment. Thank you for your attention.
Thank you very much, Philipp. So, any questions? So, maybe let me start.
There's one.
Oh.
Thank you for nice talk, but please let me ask a question. Could you show the slide where you have talked about this EPR pair for spin components? Yeah, because I would interpret this EPR experiment as for X and P as the possibility to measure X and P on extended Hilbert space for, let's say, two systems. Yes. No. Before it was the very first. Okay, this one, yeah? Here, what are you saying is that this equation where you are linking the system A and system B by a linear estimate. The problem is that this you cannot do in general, yes? Because system A and system B are different systems, they are different operators. So, in my opinion, the EPR formulation would require to find a combination of operators which commute and which are constructed on extended Hilbert space.
So this is exactly what we do here, right? So you can interpret this inferred variance here, where you subtract from the actually measured value SB, the value SA with some gain factors or so. In the case of an ideal system with ideal correlations, this would correspond for the Y components here to the plus combination, and for the Z components to the minus combination. So this would be exactly the EPR variables as considered in the original paper, the sum of the momenta and the difference of the positions, for example. And these would then live in the 4-dimensional Hilbert space of the two systems, and they actually commute. This is why this works. But the EPR paradox in this criterion is more general. So you don't have to restrict yourself to perfect correlations. You can also live with imperfect correlations. You don't have to restrict yourself to a linear estimate. In fact, you don't even need a quantum description of system A to do this. The only thing that counts is that system A has information about system B, which you can somehow use for prediction. And then this tests how good this prediction is. This was pointed out by Margaret Reed for optics first, and now is applied to spin systems.
Okay, thank you. Let's talk about this later. Thank you.
This is very established, yeah.
More questions?
Hello. In terms of the local spin rotation, could you let us know how to actually experimental implement the local spin rotation? Maybe you can remind the separation distance between two clouds. I missed the value that the separation distance
let me
between
see
clouds.
whether I can quickly show this to you. Maybe here. So how do we actually do the individual spin rotations? So once the two clouds are separated, we then apply coherent coupling pulses between the hyperfine components, either on the green spin here or on the orange spin. And it's different transitions, so we can address them, but they're also spatially separated. And on our atom chips, we have driving fields with magnetic gradients, with gradients, so we can also address them spatially. And then these are actually the local spin rotations. So this is a Rabi oscillation on the green spin, system B, without affecting system A. And this is the other way around. We can turn the spin on system A without affecting system B.
Hello. I have a question about non-Gaussian states. So you
Yeah.
said this is, of course, one direction you want to follow. Are you thinking about some deterministic evolution, or are you thinking to some heralded measurement to generate non-Gaussian state in your
So
system?
non-Gaussian states is possible, but it's not entirely clear yet whether we can do Bell with it. So we quite naturally have non-Gaussian states if we run the squeezing evolution for longer. Then we get these over-squeeze states. And in principle, if we had a perfect system, we could run this one-axis twisting even longer, and then we would have a Schrödinger cat. And so the question is, from which point on in this evolution, because the Schrödinger cat is out of reach because of atom losses, from which point on in this evolution is the non-Gaussianity useful for Bell, for example? In another way, we can also work with the Gaussian spin squeeze states if we do particle number resolving measurements. So in this paper, we actually consider parity measurements on a regular squeeze state, and that can also give you Bell in the spin system. Yeah.
So maybe just if it is very short, because we. So please.
My question: you showed these absorption images with fantastic resolution.
Yeah.
You didn't really mention any time scales. How long do your coherences live?
So the coherences live of order a second or so. And here, I don't have it here, but the challenge is that there are inelastic two-body collisions in this upper state. And then whether it's a few hundred milliseconds or several seconds really depends on what the atomic densities are and how much population we have in this upper component. And the detection is simply done by carefully tuned, tailored absorption imaging. A lot of work went into this, but the whole detection just takes a few tens of microseconds. Yeah.
So, thank you very much. So let us thank the speaker once again.